Welcome to part 2 of chapter 15. We're currently talking about soil properties starting with slide 10. Tonight we're going to start with soil texture. We see that as the texture gets larger as we go to the right, clay has, over on our left, has a very, very fine particulate, silt being the next, and sand. Of course, gravel being the largest, but in environmental, we're really interested in soil that can sustain life or sustain producers. And so when you look at these soil sizes, sand's not that big, 0.15 millimeters. So, but if you think about it, you've all had sand in your hands, you've felt it, and you can distinguish a grain of sand. Silt is a little bit finer. You're going to get to experience some clay in class that I brought from Illinois, and you cannot feel the particulates. You can feel a powder on your hand. It's like baby powder almost. That's how small it is. Now, the particulate size is important because that gives you an idea of how much pore space you're going to have. And if you recall in part 1, pore space is the area in between each particulate that can house water and or air. And both of those are important, and specifically oxygen in the air. So if you think about it, you need oxygen for the ecosystem that has been created in this soil. Anything from your moles, your inchworms, or not inchworms, earthworms, to your tiny, tiny aerobic microbes. And those aerobic microbes are doing a huge job by decomposing all of the organic matter and turning it into a very, very nice soil base. This is just in words, everything that basically I just said. When you look at different types of soil, because of the particulate matter size, you see some different physical characteristics. Think about here. Think about pouring water on the sand. It percolates immediately, doesn't it? Okay, if we go to that other extreme, if we poured that on top of clay, it would not percolate immediately. It would take a longer time for that water to penetrate down through the soil base of the clay. That's because the particulates are so close together, there's not a lot of room. I'm not saying there isn't any room, but there's not very much in comparison. Also, this leads to low oxygen levels in the soil. However, what you're going to see with clay is that clay, because clay itself is negatively charged, it'll hold on to cations. So it holds on to cations. It also has a lot of water retention. So water retention, or water, then can hold on to then the anions. And it tends to be a very nutrient-filled soil. This is just a graphic showing how here's particulate, and it has negative charge, so all the positive charged ions such as calcium, hydrogen, magnesium, potassium, they're all being held there. That's all sodium, everything that plants need. So that is a good thing. Has high nutrient retention. But if there's not room for water to penetrate and go through, that can leave you a couple of problems. It doesn't take water very well after a drought. It doesn't when it's hard and dry, it's hard to get it to soften up and take water, so to speak. And you can't get water off, and so then your plants can get too waterlogged. So those are issues with, say, working clay or a clay soil. This is the chart that we're going to be working with in our lab, as well as the soil triangle, which isn't in the notes, but we'll be talking about. And so this is just giving you sand and clay, and then in the middle loam is a mixture of silt, sand, and clay. So this is a Goldilocks scenario. Clay soil, aeration, too poor. Aeration in sandy soil, excellent, but honestly too much. And loam is just right. It's good. Drainage, and you see nothing excellent, nothing poor. But it's just right. So this is the best if you have a choice for farming, or you have a choice for gardening. You create or amend the soil to get it as close to loam as possible, because it gives you the best of both worlds, the clay and the sand. And that's what we're going to determine what kind of soil we actually have here on campus with the soil triangle in the lab. We've talked a little bit about pH, and I want to talk to you about it as far as pH of soil. Remember the range of tolerance that we talked about: too much, too little, and just right. So pH soil range, or that range of tolerance for most producers, is going to be about 4 to 8 on the pH scale. So you see slightly more acidic. Plants can tolerate more acid really than they can tolerate it being alkaline, because it only goes up to 8, 7 being your neutral. So, but that's the range that most plants like. What does a change in pH do? Change in pH decreases the ability of some plants to obtain nutrients. So it gets out of that range of tolerance, and their ability to uptake nutrients is diminished. Best, or where we see most biodiversity in producers, is in between 6 and 7. Most of them can tolerate 6 and 7. That's where they like it. That's where they will grow the best. Can you think, though, of a biome that would not have a 6 to 7 pH, but have actually a very acidic pH? We talked about it just a little bit in Chapter 6. That would be the coniferous forests, or the taiga, primarily pine trees. And the pine trees' needles, as they decompose, they're acidic themselves, and so it puts more acid into the ground, therefore creating a more acidic soil. If you look and you see pine trees, there's very rarely anything that grows underneath them. Not just because it's in the shade, because other trees can shade, but other plants will grow underneath them, but because they create such an acidic base down there. This is just showing you some different graphs here. So we have most of the range right here from 4 to 8, and then this is the pygmy forest. Thinking flowers tonight. Pygmy forest in California, and pygmy because it has little trees. What you're getting back into here is this is an ecotone, so that it's changing in pH, and you're starting to grow some others. Of course, these are pine trees, so they can handle some low pH as well. But very, very limited in biodiversity for producers. Basically, you have one plant that can tolerate that, but it uses the soil well. Then if you look on the alkaline side, that's Death Valley. Very, very alkaline soil, about an 11. Now I want you to remember, go back, talking about alkaline. Our groundwater is alkaline. It runs about 8.5. And that's because we have a limestone or calcium carbonate rock bottom. And when you watched up in the Floridan, the video, Water's Journey, that is a calcium carbonate aquifer as well. So the water runs about a 8.5, as illustrated in that stream, in the underground stream that was bubbling up to make a river in that. And so we have a lot, if you think about it, we have shells in our soil. So ours tends to be a little more basic because we do have that calcium carbonate in there, and calcium carbonate is a buffer, so it becomes more basic. Now, if you have a soil type that you don't want, and you want to amend it to make it more basic, you would add lime if it was acidic. But if you want to make it more acidic and more pleasing to acid-loving plants, then you would use sulfur, because sulfur is an acid, or creates an acid. I shouldn't say it's an acid, but it creates an acid. Okay, going back, remember the forming factors that we had. We had climate and time and type of rock. And those create, because you have a different kind of rock, you have a different pattern of decomposition, different organisms there, then we have different soil types. There are actually 12, and if you look on the poster underneath where I hang your grades, you'll see all 12. But these are ones that are very, very common, and you can kind of liken them to these different biomes, just to give you an idea, because in your biome chart, you should have done soil composition. I think that was one of the categories that you had to do. I hope it was. Anyway, coniferous forest. When I say coniferous forest, you think pine trees. Think a little acidic because of the pine trees. So that's a good for spotosol. That's a good characteristic. Temperate deciduous. Okay. High in organic matter. Lots of leaf litter. Very, very high in nutrient levels. Grassland. High in organic matter. Obviously not leaf litter, but you're going to have grass left over. And also very fertile. Deserts. Very little fertility. Very permeable, because most of them are sand. Some of them are clay. You'll get some clay in some of these deserts. So then it would not be as permeable. But either or. Excuse me. Our last one is oxasols, and that's tropic and subtropic. I want to talk about the tropical rainforest and the fertility of the soil there. Soil is not very fertile. You would think it would be, because with the temperate deciduous forest, you have all that leaf litter, while tropical rainforest for biodiversity is second to none. and there's a lot of leaf litter, but there's a difference. 24/7, it is nice and mild, and it's perfect weather for microbes. So there is a very, very rapid rate of decomposition. Plants also have a mechanism in them to where they uptake nutrients immediately as soon as they're delivered to the soil. There's no wait time with them. It rains so much there that if there was any lag time between uptake and the decomp, lots of the minerals and nutrients would be lost because they would go into the water and the water runs off. Because there's, they get 120 inches a year. That's a lot of rain. So that would be something. It does perk. It's got soil that perks, and it also does not hold nutrients for very, very long because of that ability to perk. So spogisols, alphasols, mollisols, iridosols, and oxasols. Okay. Soil erosion is the same problem. We're going to look at things that, what causes soil erosion? Because soil erosion can come from different mechanisms. It can come from the wind, it can come from water, it can come from over farming, but basically what we're talking about is leaching out nutrients. Leaching out nutrients. When we leach out nutrients, then the soil loses its fertility and nothing can grow. So we worry about that within the ecosystem because that's a base of our ecosystem. We worry about that with farming because this is where our food comes from. So, okay, looking at this, distinctive patterns here with erosion coming down this hillside. Very, very hard to have a steep grade like this and not see erosion in there. It just really is. And so we have it vertically, and these are big crevices that are made. This is just an area they can't even get grass to grow on. Another thing here, tractors. When we're disking up and plowing up the soil, we lose a lot of it in the wind. And so actually farmers at this point aren't doing this kind of farming anymore in most places. In some places, yes. And they're using a no-till method, which preserves topsoil. And we'll talk about that as we go a little further. This is your case in point, very important case in point. I want you to look at the map right now. You have seen this portion of the map, but we were looking at the Ogallala Aquifer. And when we started with water and water problems, I talked about the Dust Bowl in the 1930s, and they are suffering now what some scientists believe is a mega drought in the same area where you see the Dust Bowl. Now, we're not worried about it being dusty there at this point, because it wasn't that nature had never had a drought before in that area. There had been droughts before the 1930s. But what happened there was farming techniques exacerbated the effects of the drought. So all the soil was loose, and fly it did. It went clear up to New York City and beyond. People lost their farms, they lost their lives. It was a terrible, terrible time. And that terrible, terrible time made us realize that as a country that that we have to do something to preserve our topsoil because that is how we eat. And so this area's claim to fame was the Dust Bowl in the 30s, and in the 2000s it's going to be the lack of water from the Ogallala Aquifer because it's going dry. So in 100 years, in less than 100 years, this area's really, really taken some hits and will probably continue to do so if the drought continues on in North Texas and in this area. We're going to see a video on this case in point. This is the end of part 2.